Alright, this is my last little video. It's got other videos embedded in it, but that factor that we've talked about, how much time gets dilated by, how much length gets contracted by, how much mass gets increased by, is given the Greek letter gamma. So that's what this thing over there is. And it's got this crazy equation with square roots and squares in it. The gamma factor is equal to 1 divided by, and then all under square root 1 minus v squared over c squared. V is the speed of the object, and c is the speed of light. In air or vacuum, the speed of light is 3 times 10 to the 8, so that's what we'll be using every time we crunch this out. Basically, if I give you a v, tell you the speed of an object, you should be able to do the math and figure out the gamma that corresponds to that speed. Or if I tell you the gamma factor, you should be able to rearrange the equation and tell me the speed of the object. So it's really an equation with two things in it. If I tell you one, you should be able to calculate the other. If you're Googling this, sometimes this factor, sometimes they just call it the gamma factor, and sometimes they call it the Lorentz factor. I've got 4 examples here for you to try. Give you a speed, find a gamma, give you a different speed, find a gamma, then use the gamma. Basically in disguise, this is a gamma. So given a gamma, can you find the speed? And then, oh yeah, a cool one down here. What if you plug in a speed bigger than 3 times 10 to the 8? What I'd like you to do is go through all 4 examples. Seeing the examples will help this click, but I'm going to keep yabbering on a little bit. If you take the time and put something like this, basically our equation using y's and x's instead of v's and gammas, if you were to put this in a Desmos and graph it, take a look at the graph. It's a cool graph. You can look at it. You Desmos wizards can look at it. But really what's cool about it is that the gamma stays at 1. It's just sort of a horizontal line at 1 until we get till our x value gets to 1 times 10 to the 8. So really what that means is special relativity isn't noticeable until things are going kind of 1 times 10 to the 8, and then special relativity starts to have an impact. A worksheet with questions, a check-in related to this, a check-in to set up what we're going to do next, and then one last little thing. When Einstein wrote his special relativity, he wrote it much more academic than what we've presented it as. He based all of his special relativity on 2 principles that he called postulates. It leads to the outcomes that we've talked about, that crazy gamma equation, but basically he started with 2 principles. The laws of physics are the same and work in all reference frames. That was basically saying that relative motion shouldn't give 2 answers for the same scenario. And he said that the speed of light is constant regardless of the state of motion of the source of light and the observers. And basically pushing those 2, that's where he came up with these crazy ideas of time dilation, length contraction, and mass increase. What's really kind of weird about it all is the math behind special relativity was the easy part. It was the ideas that were kind of controversial and creative. If you're curious, here's a derivation of where gamma comes from. The hardest part of the proof is we use Pythagorean theorem and do a couple substitutions. The math isn't crazy weird. Einstein's other stuff, the math was crazy hard, but this one, the math actually wasn't all that hard. Buried in special relativity is the E equals mc squared equation. We're not going to get to it, but basically E equals mc squared is the answer behind all nuclear reactions. We can create nuclear energy at the expense of mass. So mass gets converted into joules, which is kind of cool. There's all sorts of neat things. I've read books and watched videos about Einstein. Even with more time, we would just sort of get through what we got to get through. But there's all sorts of stuff out there. There's this whole perspective that maybe his first wife was more of a significant contributor to special relativity than she gets credit for. There's stuff about him not being able to get through school. He did get through school. He got a PhD in physics. And after his PhD, he was hoping to get hired at a university, but universities didn't want to hire him, sort of politics and religion and all sorts of oppressions going on at that era. So he ended up with this job at the Swiss Patent Office. And so some people say because he got this job at the Swiss Patent Office, which realistically speaking wasn't a hard job, he had tons of free time and daydreaming. That's what gave him the sort of flexibility. to come up with special relativity. The fact that he didn't really have a lot of responsibilities and he could just kind of daydream. Also, one last thing, this thing called the twin paradox is often mentioned. If you've got a few minutes, look that one up. Okay, I'm going to pause this video. You take some time and look at those 4 examples and email if you have any questions.